So thank you for the introduction, and thank you to everyone for being here. First of all, I would like to thank the organizers for the invitation and for the opportunity to present at this very interesting meeting. Well, sometimes thanking the organizer could be seen a kind of routine moment, but I cannot do it here with a little bit of an emotion, considering that we are also here to commemorate our colleague and friend Tarek Ali, which who actually meant so much to many of us. In my case, actually, there is kind of a personal story related to this talk, because actually I discussed with Tarek the very beginning of this project 3 years ago in Bielorussia, where we are meeting for, well, one of the meetings that people in this community often attend. So we were actually having the free afternoon of the week, and we wanted to go for a walk in Bielorussia forest. And in this walk, I started telling Tarek about the results I was planning to get on this. And the first outcome is that we got lost. So we didn't manage to get on the right way to the forest. And we essentially, well, eventually we arrived, but it was a very pleasant digression, which somehow stimulated some of the work that I'm presenting to you. Another thing that I would like to make at the beginning is a little bit of an apology, like the previous speaker. It so happens that I also have to apologize for the speakers from tomorrow to the day after, the rest of the conference, because I also need to be in Hong Kong on Friday morning. So it so happens that two speakers actually have the same reason why they need to leave early. In my case, because I have to teach. Okay, so let me get started. So the title, as you see, is about some new applications of coherent states in quantum information. So the first question is like, which applications? Because there are so many applications of coherent states, and well, even within quantum information, there are many of them. So here I will talk about two particular applications that you may not be familiar with, and that's the kind of nice part of the talk, to introduce you to something perhaps new. So the first application, what I call the state transformation games, is a very broad category of problems where essentially one gives you a set of input state and the target set of a desired set of target states, and the problem is to see how well we can convert states in one set to states in the other. So here the kind of intuitive idea is like, what is the best way to turn a given input into a desired output? And this has a lot of applications, like for quantum cloning, also quantum state estimation, and other problems in quantum information. And the second application, that is the one where coherent states play the biggest role, is actually called the problem of quantum benchmarks. So whenever you have a problem like the first, when you want to transform a set of states into another, how can we certify that there is an advantage in doing the transformation coherently, using quantum operations, as opposed to measuring the input and producing an output that depends on the outcome of the measurement? So finding criteria to certify a quantum advantage is called the problem of quantum benchmarks. And here it is really nice that coherent states give us a general analytical formula for the best benchmarks that we have to use here. So let me start from the first application, so the problem of state transformation games. So I have a little bit of a cartoon here and a little bit of a story. So let's put the game indeed in the form of the game between a referee and a player. So imagine that there is a referee who prepares a quantum system. This could be, for instance, I don't know, a magnetic, the nuclear magnetic system, or could be a state of the radiation field. So the referee prepares a quantum system in some random state, so some state chosen at random, and sends this state to the player without telling which state this is. So the role of the task for the player is to return an output state to the referee, knowing that the referee will perform a test. So the referee will perform a certain test, which is known to the player, and the test in the end will assign a score, +1 if the test is passed, and 0 if the test is failed. So here is my cartoon. Here is the referee, here is the player. So the referee starts by preparing a quantum system in some state rho x. Generally, this could be a density matrix. That's why I use this notation. So then the referee will send the system to the player. The player will build some quantum machine that will perform the task of transforming this input state rho x into some output state rho tilde x. And this is what happens here in the cartoon. So after transforming the state, the player will send it back to the referee. So the referee will get a transformed state, rho tilde of x, and finally will perform a test that depends on x. So the referee knows what the state was. The referee picked rho x. So he knows that he knows the value of x, and he performs a test that checks if the output is really the output he wanted the player to prepare. So the result of the test could be, oh, I wonder whether I can, great. Okay, that's beautiful. So the result will be either that the test is passed or that the test is failed. So two possibilities, and this is a probabilistic process. So practically this is a quantum measurement that the referee will perform. So let me formalize a little bit this cartoon. So the mathematical formalization is as follows. So we have the random input state is an ensemble of density is described by an ensemble of density matrices. So we'll have the state rho x with the probability px, and x will vary in some set of parameters that everybody knows is part of the specification of the game. So the referee and the player know the set of possible states, and they both know what is the probability that the referee will use to choose this random state. So the test is a binary POVM so there are two positive or two non-negative operators, Tx and identities minus Tx. So the referee will perform a quantum measurement described by this binary POVM. And the average payoff, so the amount of, the score that the player can expect to win, is the average over x of the probability that the test will be passed. So the probability, this is the trace of the test operator Tx with the output state, rho tilde of x. Is there any question so far? Sorry? POVM. Oh. So that's for positive operator valued measure, which means it sounds a little bit ridiculous here because it's like a set of two operators. So it's kind of a little bit of a Baroque way to call a collection of two positive operators that sum up to the identity. I will use it a little bit more later, and then I will really have an explicit definition. Thanks. Is there any other question so far?
Just the meaning of tilde again?
Tilde is just to say the output. So in the cartoon here, there was rho x was the state that the referee gives to the player, and then the player will transform it into rho x tilde in some way. So this is the state that the referee will get back, is rho tilde of x. So it will measure that and pass or fail. So okay, this is so this specifies the game. Because there is some process happening in between. Sorry?
Another system of density matrices?
Could be another system, could be the same system. It depends on the particular game that they're playing. So it depends on what test the referee is performing in the end. The test could be a test on the same system, and then rho tilde of x would be a state of the same system. And of course, the player has to choose the state that maximizes the probability of success.
This looks like some generalization of quantum mechanical scheme.
Of what, sorry?
What you write is some generalization of quantum mechanical system given by John von Neumann, as I understand.
Oh, I'm using the description of density matrices. So what we have here.
Introduce a system of density matrices. So you have many quantum systems.
Well, no, we have one system that can be in one of these density matrices.
You have many density matrices.
Yes. So we choose one at random from that. It's like tossing a coin. There are two possible outcomes. Sorry?
What is quantum observable here?
Well, there is a test. So this POVM will describe a measurement.
What is measurement? Measurement is the same as quantum observable.
Yes.
Some
yes.
positive operator valued
Yes.
measure, spectral measure.
Well, yeah, doesn't have to be a spectral measure. This is a positive, is a general positive operator valued measure. It doesn't need to be spectral, but it describes a quantum measurement that in principle you can do in the lab in the canonical way.
What you present is inside the framework of Alexander Kolevo's book.
Yes, sure. This is, this is probably a good reference for all. This is Elstrom, Kolevo is like, or also, sorry, Belavkin also had done some pioneering work on these things. Is the framework of quantum statistical decision theory. Yes. Thanks. So yes, this is not necessarily a spectral measure, but we can enlarge the system and realize it with a spectral measure if we want. But here I will just take the POVM framework for granted. So let me give a couple of examples of this general problem. So one problem is just to preserve a pure state. So the referee will prepare some pure state, some rank 1 density matrix, and the goal of the player is just to keep it there, not to change it. So this test tells us that the referee in the end will check if the state is still the same by projecting on the projector on that state versus the orthogonal complement. So this is really a canonical measurement, as you were mentioning. Actually, most of the measurements I consider here are actually projective for the test. So this here is just the game of getting a state from the referee and not changing it, trying to keep it stable as much as possible. Another game is to make copies of a quantum state. So you can imagine that we have n identical quantum systems, and each system is in the same state, same pure state psi x. So here the goal would be to prepare more copies, so to go from n copies to m copies. So the referee will make a test on m particles instead of n, and the test is designed to check if the player was able to make copies or how well he was able to do it. So this is an important problem in quantum information, is the problem of quantum cloning. And it fits the kind of general framework that I was describing in the previous slide. Another example, perhaps more related to physics, is about amplification of coherent states of the radiation field. So you can imagine here that you get a pure coherent state, like of the harmonic oscillator, and you would like to amplify the signal. So you would like to have a coherent state with the same phase, but with a bigger amplitude. So from alpha to g times alpha with some gain factor larger than 1. So the referee will make a test to see if you have been able to amplify in the desired way. So this is another game that one can try to play. For these two games, actually, we know in advance that we cannot succeed with probability 1, so we cannot make perfect copies and we cannot amplify perfectly. But that's why the framework is interesting, because the framework is about finding what is the best way to achieve these tasks that are actually impossible if you want to do it exactly. Okay, so these are examples. So let me again formalize a little bit. So the player will use a strategy. So she will try to maximize her payoff. So the question is like, what is the best strategy? So here a strategy will be a physical transformation, then transforms the input state into the state of an output system. So mathematically, this will be a completely positive trace-preserving map from the states of the input system to the states of the output system. Again, to connect with kind of more familiar framework, this map will describe an open system evolution where we let the input interact with some ancilla that we use to help the transformation. So the system will interact unitarily with the ancilla, we'll get the output, and in the end we discard the ancilla. If you look at the evolution of the open system, you get a completely positive trace-preserving map through this physical picture. So the output state, one of the questions before, so what is rho tilde of x, is the action of the open system evolution applied to the input state. I'm sorry?
Not enough to have positive.
If we think of the interaction picture where the system interacts with an ancilla through a unitary evolution, so we have a kind of... Yeah, I mean, it follows from this physical picture. If you ask that you have an interaction of the system with the ancilla, and this interaction is unitary, so they evolve unitarily together, the resulting map is completely positive.
So for unitary evolution, it's completely positive.
Yes. Well, the important thing is that the system and the ancilla should start without correlations. So if I start with the state of the system here and I prepare independently the ancilla, the two evolve unitarily, then I will get a completely positive map.
Closed systems.
Sorry?
You are interested in closed systems.
Well, this completely positive map is for open systems, but the evolution of the system and the ancilla together is closed. So this is the effective evolution describing what happens to the system when I couple it to an ancilla. Yes, when I couple it to an ancilla, and the two evolve unitarily together. So this is what we get from this type of physical picture. Okay, so we get our output state. So the maximum payoff, if I substitute now, so this will be the maximum overall completely positive trace-preserving maps. So physically, the maximum overall possible physical transformations of the probability that the output state, so this state transformation applied to the input, will pass the test. So this is the probability of passing a test averaged over all possible states that the referee could have prepared. So this is an expected value of the payoff. So this is the quantum value. So the first result that we had is an explicit expression for the maximum payoff. This has nothing to do with coherent states yet. This is this is for every state transformation game. So let me parse for you this expression. So this tells you that the maximum payoff is given by the maximization of a norm. So this will be the operator norm of an operator that we have here, where, so this operator consists of two parts. So we have omega. Omega here contains all the details of the game we are playing. So you can see here we have the input state, rho x. We have the probability of choosing rho x, and we have the test from the operator from the test.
X belongs to bonded operator.
Which?
Rho is traceless.
Yes.
X is bonded operator.
T of x, yes, because it's smaller than the identity in operator order.
Which kind of tensor product?
Yes, the usual tensor product of two separable Hilbert spaces.
One norm and take the product of these two Banach spaces.
Well, Hilbert spaces would be L2 norm. I'm sorry? I mean, this. I mean, yes, we have two Hilbert spaces for two physical systems. So these are like L2 functions, for instance, over some set. And we take the tensor product Hilbert space. I know only one definition of tensor product Hilbert. Sorry? Yeah, these are operators on the tensor product Hilbert space. Sorry, just to make it simple, why don't we think about finite vector spaces, finite complex vector spaces? And this is a matrix, and I think we all agree on the Kronecker product. Sorry? I'm sorry?
This problem does not exist in finite dimensional case.
The one you ask.
Well, it doesn't matter which norm you take.
Yeah. Well, no. Sorry, you have different norms also for matrices, and here there is a big point about which norm we use, because they will give different the solutions to different problems.
So finite could be where this finite dimensional case.
I'm sorry?
Now we will prolongate your talk in the case of finite dimensional.
Just for the sake of being able to get to the end, because if we will have to argue about what is the tensor product of two Hilbert spaces, I doubt we will ever get to the end. So actually, I would say that most of the results are actually more clean and more rigorous for complex finite dimensional vector spaces. Okay, so let's think of this as matrices. This is the Kronecker product of two matrices, like elementary school Kronecker product, for some of you at least. So we do this, so we take the product of these matrices. The important thing is that here you have all the specifications of the game put together in a matrix. And well, really, I hope that some of you can also see what is this in infinite dimensions. It's an operator acting on a tensor product space. And here I have to compute the operator norm. Since this operator is positive, this just means the maximum over the expectation values. So this is, here I have a positive operator because everything in the sum is positive. And I forgot to say, so here we have the maximization essentially over a density matrix that has full rank. So I have to take the inverse and take minus one half of that matrix. This will give this operator. So the operator norm of this particular operator is the maximum value, is the maximum probability of success in the game. So the fact that we have operator norm here actually is very important. So it's important that we compute this quantity and not, for instance, the Schatten 1 norm. That would give a different value. So here, I mean, even if we are in finite dimensions, different norms have a different operational meaning in this game. So this result was found with my student Giulio Chiribella, but actually before us it appeared in a different form already in this work by Koenig, Renner, and Schaeffner. So what do we do with this? So there is another thing that we can do. We can play the same game as before, but now the referee gracefully grants the player the chance to pass in the game. So the player will have the chance to say, okay, sorry, not this time. We will play another timer. Let's do it again. I'm sorry? Yes? Do you really want to see the results of this talk, or should we talk about gender equality and other important matters for sure? Okay, so there is a strategy. The strategy now is a probabilistic operation. So this will involve a measurement. So in a cartoon, this will be an evolution that sometimes will give an output and sometimes will give a failure message. We'll say, okay, sorry, we didn't get what we wanted, so we'll play another time, not this time. So mathematically, this is still a completely positive map, but now it's not trace preserving, it's trace non-increasing. To point to a reference, you can think here of the work of Krauss, Ozawa, who discussed about the description of the measurement process. So this is an example of like a two-outcome measurement where one outcome is failure and the other is success. So conditional on success, we will have a physical transformation. So we can compute what is the probability of winning in the game on the condition of playing the game. So we have to rescale by the probability that we actually stay in the game. So if we take the conditional probability, we will get a different value now. And the beautiful thing is that the expression for the maximum payoff has still the same expression, but now it's easier to compute because we don't have to minimize anymore over the density matrices. So we still have to compute an operator norm of this operator, or this matrix, if you want to state infinite dimension. But now we don't have to optimize anymore over the density matrix that we had here. We have a fixed density matrix. This is the average density matrix of the ensemble that was used by the referee in this game. Okay? So this is the same expression as before, but before there was a minimum overall density matrices here. In the probabilistic case, when we are allowed to pass, we just fix a particular value, a particular density matrix here, namely the average density matrix of the whole set that we are using in this game. Okay, so now I can give you an example, a concrete example of this game, about amplifying coherent states of the harmonic oscillator. So here, well, we have the familiar coherent states. And what we want to do, ideally, is to transform a coherent state alpha into an amplified coherent state G alpha, where G is the gain of the amplifier. We would like this to happen for every possible value of alpha, for every complex value. So in a cartoonish expression, we would like to go from a laser light with a certain phase and certain color to a lot of laser light with the same phase and the same color. Okay, this is what we would like to do. Oh, I skipped probably one step. So, well, one thing is that we want to do this for every value of alpha. More realistically, we could have a prior distribution over alpha. We can choose this to be a Gaussian in the complex plane. So the values of alpha that have a smaller amplitude will be more likely to appear here. So the referee will be more likely to pick values of alpha that have a small expectation value of the number operator. So here, if we have this Gaussian with the parameter lambda, so lambda actually describes our information about the prior, describes how much we know. So if lambda is equal to 0, this Gaussian is flat, so we have no information. If lambda is equal to infinity or goes to infinity, the variance of this Gaussian becomes small. It means that we actually more or less know what state is being prepared by the referee, namely the vacuum. Okay, this is about modeling the source. So now the important thing is that we cannot amplify coherent states perfectly. So there is no way to implement this transformation exactly for every coherent state alpha. And there are very good reasons for that. If we could do this, we would violate the uncertainty principle, we would communicate faster than light, we would violate the no-cloning theorem, we would violate more or less every sensible thing we can imagine. So the list goes on. So this cannot be done exactly. The question is like, what is the best approximation of this impossible operation of amplifying coherent states? What is the best physical process that is still allowed by quantum mechanics and approximates this transformation as well as possible? So there is a physical way to do this by using two-mode squeezing. So you can couple your system with the vacuum, let them interact together, and then this will give the physical evolution. This is exactly what I was saying before in an abstract way. When you couple the system with an environment and they are independent, when they evolve unitarily, the resulting evolution is completely positive in this model. So this is what we get here. So what we get is actually, from this scheme, is actually a mixed state in the output, which is displaced by a bigger amount G of alpha. So we are able to displace the state more, but the price we have to pay is to go from a pure state to a mixed state. This is what we can physically do in the lab. So it turns out that, so using the results that I showed to you before, this is the best physical process that we can use to amplify coherent states. Because indeed, if we phrase the problem as I did before, you will find that the probability of passing the test by the referee will be given by this expression, depending on the value of the parameters. And when you don't have too much information, when lambda is not too big compared to the amplification gain, this will give us this expression, which can be obtained by using the parametric amplifier. So that's pretty standard, is nothing particularly strange here. So what is interesting is if you allow to pass in this game, you get a very different situation. So if you allow the player to pass and sometimes to say, no, I don't want to play the game, you can even approximate a probability of success equal to 1 in the limit, which is almost paradoxical, because it is physically impossible to transform alpha into G alpha for every alpha. But if you allow your probability of success to become arbitrarily small, then it is possible to succeed in the transformation almost perfectly. So here there is a critical behavior depending on the value of the parameters. So if we have enough information about the parameters, so if the variance of the Gaussian of the prior distribution is small enough, here we become able to asymptotically approach a probability of success equal to 1 in the game. If we don't have enough information, we'll still have this value. If you have a good memory, you may remember that this is the same value from the previous slide. So for some value of the parameters, there is really no difference between probabilistic and deterministic operations. But if you have enough knowledge of your state, then you can do strange things. You can approximately achieve almost a perfect transformation, almost a perfect amplification. So the important thing, as I said, is that we need to have some prior information. If you take no prior information, if you have lambda equal to 0, then there is no difference between deterministic processes and probabilistic processes. So you always get the same value if lambda is equal to 0. Is there any question? I saw.
Better not to ask.
Better not to ask, otherwise we really don't get to the end. Okay, so this has actually been approximated operationally in the lab. This was proposed by Timothy Ralph and Jeff Lund in 2008. So independently of the work we did, there was already one way to achieve this almost perfect amplification. So the process, well, they have a physical process to do it. Here I just give the mathematical expression of the map. This is something like this. So it has a truncation, and for large n, this is almost perfect. The caveat with the scheme is that the probability of success goes down exponentially. So there are experiments on this, but in the experiments, well, the experimentalists had to use pretty small values of the amplitude of the coherent state, and for those values they could show a very precise amplification, but only for the small values, because otherwise the probability to see this transformation happening becomes exponentially small. Okay, this is this is a list of papers, of experimental papers where this probabilistic operation has been physically implemented. So this one was the one we also analyzed later. This was in 2010, as far as I remember, about realizing approximate probabilistic amplification of coherent states. So now, I think I have how much time? Like 15 minutes. 15? Oh, that's a lot. I thought I had 5. Okay, so I was prepared not to be able to get to the end, and I will still not be able to get to the end, but I will at least... It depends, yes, it depends. Okay, so I can get to the point that I think was the most interesting for the point of view of coherent states, because here really coherent states play a major role. So what is the problem here? So imagine that you want to implement a physical transformation, like you want to play the games that I was talking about before. You want to play a state transformation game. So you go to the lab, or somebody goes to the lab. Oh, this is the answer why it was a she, because, yeah, in this picture is a woman. So, yes, you go to the lab, you want to implement the optimal transformation, but actually in the lab things are messy, so you'll never really be able to implement the optimal transformation. So how can an experimentalist prove that she implemented, she realized a machine that had a quantum advantage, that did something that could not be done by transforming the states in a classical way? So since there are imperfections, you cannot just say that you reach the optimal value of the payoff or the fidelity called here. So you need something else. So the idea here is to compare with classical strategies where you measure the input and prepare the output in a state that depends only on the outcome of the measurement. So in my cartoon here, so here is the input state rho of x. Imagine that you apply a quantum measurement on this, so you'll use some measurement scheme, and this will output some value, some outcome y. So there is no quantum system anymore, or if there is one, you are not caring about it anymore. So after the measurement here, you only care about the outcome and leave all the rest, there. So there was an input system, now there is only an outcome of the measurement. Yep?
Sorry, you need to be a bit clear on the verification. So this is a verification step independent of the player who you're testing.
This is one way to play the game, by using a measurement.
The player's like a prover. Says
The referee is like, yes, sorry, the player is like a prover. Yes, yes.
This is a verifier. This is the verifier's hands, is that right?
No. This is one way the player could play. Could either play by performing a coherent quantum evolution or play by using a measurement. We want to compare two different ways to play the game and see where there is the gap between them.
Where did rho come from in this?
Oh, rho is still provided by the referee.
But the referee can purify it and keep shares outside. So
Yes. Yeah.
that rho cancers with the rest of
No. The referee could still keep part of rho. I mean, this is just about how the player could play. So we want to see a difference between two different ways of playing the game. The quantum version, the quantum way and the classical way. So we want to see what is the gap between classical strategies and quantum strategies, because the gap will give me the benchmark that I have to overcome in order to claim an advantage from quantum strategies. So this is what the player could do, could use a classical strategy. So after there is an outcome, the player could use the outcome to prepare the output state. So he could feed this into a machine that uses the value of the outcome, and this will produce the output state rho tilde of x, so the output of y, sorry, the output that depends on y. So the important thing compared to the strategies that I described before is that the input and the output are disconnected by a classical outcome in between. So we are transforming the state by first doing a measurement and forgetting about all the rest from the point of view of the player, of course. Okay, so these are classical strategies. I want to see how well we can do in a classical strategy. So we can formulate this mathematically as well. So the measurement here will be described by a P of M. So there was a question before. Now here I have the explicit expression. So this is a collection of positive semi-definite operators that sum up to the identity. They don't need to be orthogonal to each other. It doesn't need to be a projective measurement, but this is like a general measurement that we can perform. And the strategy of the player will be to measure and to prepare a state that depends on the outcome of the measurement. So this is called a measure and prepare quantum channel. So you see here that with this probability, trace of py with rho, with the input state, the player will prepare the state rho tilde of y. So given the outcome of the measurement, with this probability, there will be some state preparation happening. Okay? So this defines a particular type of map that corresponds to a classical strategy. And now we want to find what is the best payoff that the player can get by playing a classical strategy, by only doing a measurement without using a coherent quantum evolution. So the best we can get is the supremum over all possible measurements and over all possible state preparations of the payoff. So here you see this is the payoff. So with probability x, we had the state rho x. The state gets measured. So with this probability, trace of py rho x, we will get the outcome y given that the state was x. And then if we get the outcome y, we will prepare the state rho y tilde. And the probability that we pass the test of the referee is the trace of the test operator tx with the rho y tilde. Everything averaged over x, because we don't know the value of x. The x is chosen randomly, so we will average this. So this is the payoff that the player will get by playing a classical strategy. And we want to maximize it over all possible classical strategies and see what is the best that a classical player can do. So this is what is called the quantum benchmark. So the problem of quantum benchmarks is to compute this maximum value so that we know what is the best we could have done classically without using coherent interactions from the input to the output. So now it happens that we have an explicit expression for the benchmark. And again, this is a norm. When I said before the norms are important, this is a different type of norm, which is technically known as the injective cross norm. Practically, for positive operators, as the one we have here, for positive matrices, this is just the maximum expectation value on product states. Okay? So the norm we had before was the maximum expectation value on like every state. This is the maximum expectation value of our positive matrix over all product states, so like phi tensor psi. This is shorthand for the tensor. So here the norm really matters a lot, because if you change the norm, you will get the maximum payoff for a different type of strategy. So if the strategy is quantum, we had the infinity norm, the operator norm. So this was the supremum, the maximum over all possible vectors. And now if the strategy is classical, we have the cross norm. This is the supremum only over product states. So different norm corresponds to a different physical way to play the game here. And finally, I think this is the first result that was genuinely only our result. Okay, so this is the abstract result for every type of game where we want to send an input to an output. The expression, sorry, I don't know if you still remember this. This is the same expression that we had before. So this is the same operator, the same matrix that we had before, the same minimization. We just changed the norm here. Yep. Yes.
Rho is the average.
Which row?
C of rho. Rho
No, this rho is just a generic density matrix. It's just a way to define a map. It's not the average state. Sorry, that's a little bit of an inconsistent, because before I used the rho as the average state. Here I just meant a generic density matrix. It's just a way to specify a map by saying what it does on the input. Thank you.
When you maximize over all possible choices of capital Y also?
Yes. Yes. Thanks. I should have written this. Yes. Yes, implicitly here the maximization over the measurement includes the maximization over all possible outcome sets for the measurement, so also maximization over Y. Thank you. I should have better written it here. Okay, so there is the same, if you allow also for probabilistic strategies, so if you allow the P of M to contain one outcome, sorry, that's a typo, this should have been, sorry, it's not a type. So if you have one outcome that says, I will pass, I will not play the game, so the P of M has one more outcome, in which case we don't play. So if you compute now what is the maximum payoff conditioned on the fact that you play the game, so you restrict only to these outcomes, you get again the same expression, where now we don't maximize anymore over the density matrix, we have really the average density matrix of the ensemble, and again we have the cross norm, because this is for a classical strategy. So the last 2 minutes are probably to give you the formula that make this exciting for me in terms of regarding coherent states. So this expression for the classical, for the quantum benchmark, for the best value you can get classically, so this value has particularly nice expression for coherent, for Gilmour-Perelomorph coherent states. So these are states generated by irreducible representations. So here we have an input state and an output state that we want to obtain in our transformation. So here we define the input and the output states. So these are two different coherent states for the same group. They are mutually coherent if the tensor product of them is still a Gilmour-Perelomorph coherent state. So if these two states still belong to an irreducible representation. So this is a definition, and okay, let me skip the cartoon. So this is the same thing, but now we put coherent states in the input and in the output. So for this case, we have a beautiful expression that is valid for every group representation, provided that we have, for every group and for every group representation, provided that the set of input states that we have and the target states are mutually coherent with each other. So there is a kind of canonical way to compute the quantum benchmark for every group and for every representation of the group, provided that the states are coherent to each other. So I had a lot of elaboration of this to show all the application and all the rest. I think I should better stop here, so that if there is any question or clarification on what I said, we can just discuss about this, and I can maybe mention the examples that I had later in the remaining slides. So thank you very much for your attention.
Questions? This formula, I don't understand the last formula.
Yep. Yes.
But coherent states, in sense of Chiribella, they are orbits in
yes.
representation. So
yes.
We integrate over the group quotient by stabilization.
Yes, yeah, that's a very good point. So here I've been a little bit lazy when I defined them. I defined them in this way, just over parameterizing. So there will be some states that are actually equal here, because they will like hitting like the same value when you have the
means that you obtain irreducible representation.
Yes, that's why this is a definition.
The sense of Chiribella are defined for reducible representation.
I'm sorry?
He defines this state taking irreducible
Yeah,
representation.
indeed.
Yes. Take the product, first of all, is that parameterization, because you parameterize by element of group. But
yes.
It's necessary to parameterize by element of quotient space.
Yes, but to be simple here, I think it's just easier to parameterize with the elements of the group. Plus, as you said, it doesn't happen always that the product of two families of coherent states is still an irreducible representation. That's why this definition is important, because our result holds when the product is still an irreducible representation. So that's the definition. So when this is true, we can apply the result. And there are a lot of cases where this is true, indeed. Otherwise, it wouldn't be interesting to see the result. Can you mention a few of them?
No, but some repet is not true at all.
Not all. All where this is true. I mean, that's the theorem. If these two are mutually coherent, then this is the benchmark. Mm-hmm.
Just a comment. In some cases, you can integrate on the whole group when you have a square integrable representation.
Yes.
Like for the affine group. Yes.
Yes. Yes. Well, indeed, this is. Yeah, this is. I mean, yes. Sorry, I have been maybe too enthusiastic in saying all group, like all cases where the integral can be done. So this must be square integrable. I mean, of course, otherwise these two things don't make sense. So I'm talking about square integral representations of the group. Yeah.
And I suppose the representation is unitary.
Yeah. Yes. Yes. Again, a little bit of a hurry here. So yes, this is a unitary irreducible representation, or projective unitary irreducible representation. Yeah.
So this benchmark formula you have, so what I find intriguing is that it's doesn't seem to be symmetric with respect to phi and psi.
Yeah.
Whereas
yeah.
the assumptions seem to be symmetric with respect
now
to
the
phi
difference is that that phi is the input.
Okay.
And psi is the output.
All right.
So you get a phi of g, and you would like to produce psi of g.
All right, okay.
And the probability of success in doing this, the quality of the approximation, depends on the ratio between these two integrals.
All right, okay, thank you.
Thank you.
So you studied the probabilistic processes
Yep.
and the deterministic processes.
Yes.
I was wondering whether when you find the result about one, you can deduce something about the other.
Yes. Thank you. I mean, these are many of the details that I had somehow to gloss over because I was now a little bit in a rush. So this value is actually for deterministic. And in this setting, if you don't put a prior, so it's like here we are thinking ideally that we have a flat distribution, whatever this means when we have an infinite space. But in general, so this would be for deterministic ones. Then we also have a result for probabilistic. This is a generalization of this where you put the probability in both in the integrals. You put the probability of preparing the states. And of course, the probabilistic benchmark is an upper bound to the deterministic benchmark. So if you are allowed to pass, you can do better in general than if you have to play the game all the times. So probabilistic benchmark is kind of a stricter criterion if you want to demonstrate that an experiment had an advantage over classical strategies, because this is really the maximum you can get even if you are allowed to pass. And yes, so the probabilistic benchmark is even kind of neater than this one because it has the probability distribution over the input state here, while here I had to gloss a little bit over some details. Yeah.
The last one. Yeah, I have one very short question.
Yep.
Can you show one of the examples?
I had tons of them, but
The easiest one.
what is this one? Let me see the first that appears here. Oh, that's nice. So this is one, we have many copies, like n copies, of an unknown quantum state for a finite dimensional system. This could be a 2-dimensional, 3-dimensional, 4-dimensional, n-dimensional system. So you have n copies of this, and you want to make m copies. You would like to increase the number of copies, or keep it the same if you want m equal to n. So the quantum benchmark here has this very nice expression, because it's like, well, because it's simple. So this gives you the best payoff that you can get by classical strategies. So this can actually be used to certify experiments where we try to implement this transformation using using quantum resources. And if the payoff in the experiment is larger than this value, we can claim that the experiment demonstrated the quantum advantage. So,
The dimension of the space?
sorry?
The dimension of the space?
Yes, it's finite dimension here. So we get this so for 2-dimensional system, we have only one term in the product. It will be n plus 1 divided by n plus 1 for dimension equal to 2. This is like the benchmark one has to overcome in order to show that there was a quantum advantage. So an easy example, the one that motivated the whole program, is the one of n equal to 1 and m equal to 1. So just keeping the state there, have just one physical system of dimension d. just try to keep it there for some amount of time without the system decohere. So you try to implement some quantum memory or some quantum protocol that keeps the state there. So how good is the protocol? Sorry? How good is the protocol? So one way to judge how good is the protocol is to compare it with what we could do by just measuring the state, storing the outcome of the measurement well, writing it on a piece of paper and re-preparing the state after. So this somehow gives the criterion for this type of experiment. Thank you.
There is a last comment by...
Oh, no, it's a joke.
Yeah?
Can you apply your formalism to the referring process when you submit a paper to a referee?
You can check if the referee really used the quantum resources or did the referee it in a purely classical way. Frankly, considering the referee reports I receive, you should just check if the referee read the paper classically or whether just output something different. So this would be a different map. Where is it? So instead of this, it will be a measurement with a constant outcome. So it's just trace over the system. And then a state preservation that is even independent of the outcome. This is what we often get with the referee reports. So it's pretty much independent of the actual content of the paper many times. Okay.
Okay, so let's stop here and we resume at 11.
Thank you. Thank you.